Hey guys, so I finally finished chapter 4. We're now moving on to chapter 5. It's pretty exciting. Chapter 4 seemed to go on forever. I will say most students find chapter 4 and 5 to be kind of the two biggest and hardest chapters of the semester. So if you can survive and get through these, then you're doing great. If you like math, that's what chapter 4 and 5, it's just all the math really gets to people. If you don't like math, just survive it, and I promise the class gets better after that. So we're talking about thermochemistry, which is basically how thermodynamics and changes in energy applies to chemical reactions. So first of all, as you read through the beginning of the chapter, it gets into a lot of stuff about energy and work and heat transfer and all that kind of stuff. You do need to read through that. You need to know the difference between kinetic energy and potential energy and all that. I'm not going to really dive into all that stuff. I will say, definitely need to know the equation. Kinetic energy equals 1/2 mv squared. For the most part, you're going to have to do that with master and chemistry assignments and stuff like that. I don't tend to focus on that in class, and it probably won't show up on the test. It's more of a physics kind of topic, just the idea of what energy is and how you calculate that stuff. But I will say the important thing there are the units that we use. When we calculate energy with this equation, the mass has to be in the base unit of mass in the metric system, which is actually the kilogram, and then the velocity is in meters per second. So if you use those units and plug into that equation, we get the units for our energy of kilograms meters squared per second squared. That complicated thing, we simplify it down. That's the definition of what 1 joule is, okay? A joule is a kilogram meter squared per second squared. Comes from that equation. All right, now there's another unit of energy that we may talk about later towards the end of the chapter. In everyday life, if you're talking about nutrition, if you're going into any kind of dietetics or nutrition type fields, physical therapy, and that kind of stuff, you deal with how many calories are consumed in our daily diets. So the relationship between joules and calories, there is just 2 units of energy. The relationship is that 1 calorie equals 4.184 joules. That's a relationship that you definitely want to remember. That number, 4.184, is going to come up in a couple of different ways during this chapter. So thermodynamics is the physics topic of studying how energy and work are related to each other. So when we have a chemical reaction that involves an energy change, which pretty much all chemical reactions are either going to release energy or absorb energy, that's where we get into thermochemistry. And basically understanding how thermochemistry works is really important if we want to be able to understand why some reactions work better than others, and if we want to be able to use chemistry in our daily lives, kind of like burning gasoline in a car to make energy to make the car go. Let's define a reaction that gives heat off to the surroundings is defined to be an exothermic reaction. A reaction that absorbs heat is an endothermic reaction. So basically from that, we need to recognize, first of all, that the first law of thermodynamics, again in physics, we learned that the amount of energy in the universe is constant. Energy cannot be created or destroyed. So basically what happens is energy can be converted into different forms. And if you're studying a certain system, meaning a certain sample, and if it loses heat, the heat doesn't just disappear. When a sample loses heat, the heat is released and the surroundings have to absorb the heat. Okay, so the heat is always present. It can change forms, it can change places, but it's still present. Okay, so that is called the law of conservation of energy, and it can be stated by this simple little equation. The symbol delta in chemistry and physics always represents change. So the change in energy of the universe is 0. There's a constant amount of energy present in the universe. Now, just perspective-wise, looking at this diagram, on the left-hand side it's showing that we have a system in the box, and if energy is going from inside the box out of the box, that means that energy is being released by the system to the surroundings. That's an exothermic reaction. We could say that the energy of the universe doesn't change, but the energy of the system is going to be negative. The system is losing heat. The heat goes into the surroundings, so the surroundings are gaining heat, so the change in energy of the surroundings is going to be positive. The loss by the system and the gain by the surroundings are equal. You can talk about this like if I'm playing poker, and let's just say during a poker game, I win $50, then I know that there's somebody else that must have lost $50. Okay? Because the amount of money in the poker game is constant. When the other person I show up, we put a certain amount of money in the game, and when we leave, all that money should be accounted for. Okay? Now, if we do endothermic, it's the exact opposite of exothermic, so I'm not going to talk through that one, but I think you can handle that. So, a chemical reaction, basically anytime we do a chemical reaction, there's always going to be a change in energy. It could be endothermic or exothermic. When we study a reaction, we consider the molecules that are reacting, the ones that are directly involved, those are the system, and everything outside of those atoms is going to be the surroundings. Okay? Now, often we're going to do reactions in a solution where we have two things dissolved in water. When we mix them together, the molecules reacting, again, are my system. And let's just say if it's exothermic, if it releases heat, the heat usually doesn't get away and go wherever it wants. It's going to be directly absorbed into the solution. And then what we're going to observe, if we are studying the solution, we're going to notice that when it gains heat, the temperature of the solution is going to go up. So if we have an exothermic reaction happening in a solution, the temperature of the solution will go up. If we have an endothermic reaction, that means the reacting atoms and molecules are going to take heat in. They take it from the solution. So if the solution's losing heat, then the temperature of the solution is going to go down. All right, so that's kind of important for the experiments that we're going to see and for the problems that we're going to do. So we get this simple equation at the bottom that we're going to use in some of our problems where, again, playing poker, if I gain $50 and somebody else has to lose $50, the amount of money that we gain and lose is equal. But one of us, if I'm gaining money, that means that my change is positive. The person who's losing money, their change is negative, but they have the same value. Okay? That's what this equation says. The change in energy of the system, whatever number it is, it'll be the same as the change in energy of the surroundings, except if one of them's positive and the other one's negative, then you have to change the sign of one of them before you can set them equal. So now we're going to get into actually doing experiments where if I am going to study the thermodynamics for a chemical reaction, that process is called calorimetry. And basically the idea is I'm going to do a reaction in a container. As the reaction occurs, I'm going to measure the mass of everything in there and the change in the temperature from before the reaction to after the reaction. And once I have all those values, then I'm going to be able to calculate how much energy was released or absorbed. Okay, so for an exothermic reaction, we know that the heat energy that's released is absorbed by the surroundings. Typically, we're measuring the temperature of the surroundings, so we have to keep that in mind when we're doing our calculations. So, if you go to a fancy Ivy League school that has lots of money, they have all kinds of endowments and grants and all kinds of stuff like that, they may be able to afford to buy you a really nice calorimeter like the one pictured. It's a container where you can do a chemical reaction in the container. The heat that's released by the reaction, if it's exothermic, can go into the solution that's around it. They even have a fan up there to make sure that all the water is moving and the temperature stays evenly distributed. And then we have a thermometer to measure the temperature. It's an insulated container so that hopefully no heat gets in or out of the container. So it's basically like a real fancy cooler to do the reaction on the inside. So if you are at UNG and you're doing lab here, we do not buy the $1,000 calorimeters. We get a slightly cheaper version. It looks a lot like a styrofoam cup, but don't worry, we're not that cheap. We give you 2 styrofoam cups, and you can put one inside the other, and then that's the container that you're going to use to do your reactions. Luckily, having styrofoam cups it's an excellent insulator. So for the most part, when we do a reaction inside the cups, it does a good job of keeping the heat in, and our results that we get are pretty accurate. So how do we do our calculations? So we perform an experiment, we measure the mass, we measure the temperature. What do I do with those numbers? Well, there's a pretty simple equation that's going to be the basis of most of what we do. It's shown Q equals MC delta T. Q stands for the amount of heat that's either being gained or released by a system. If Q is positive, that means the system is gaining heat. If Q is negative, that means the system is losing heat. Okay. M stands for the mass. It's typically given in grams, but it does the units of the mass and the units of specific heat have to match each other. Okay, so M is mass, usually in grams. C stands for the specific heat of the substance. Every substance has its own specific heat. The definition of what the specific heat is, it's the amount of heat that it takes to raise 1 gram of a substance by 1 degree Celsius. Okay, so again, every substance has a unique specific heat. For water, it happens to be, if you remember the number I gave you for converting calories and joules, 1 calorie is the amount of heat that it takes to raise 1 gram by 1 degree Celsius. So the specific heat in calories is 1 for water. The specific heat of water in joules is 4.184. Okay, and we write that is 4.184 joules per gram per degree Celsius. That is the normal way that number will be written. Okay, now sometimes if you look in a reference book or an appendix, it'll list the same number, 4.184 joules per gram per Kelvin. Okay, now that's actually the same thing. It throws people off, but when we do these problems, a lot of times part of the equation is going to have a delta T in it, which is the change in temperature. So let's say we do a problem or do a reaction, and the change in temperature, it goes from 25 degrees Celsius to 30 degrees Celsius. If you subtract the 2 temperatures, that's a change of 5 degrees Celsius. If you switch the temperatures both into Kelvin, 25 degrees Celsius becomes 298, 30 degrees Celsius becomes 303. If you subtract them, you still get that the change in temperature is 5 Kelvin. Okay, so the change in temperature, whether you're in Celsius or Kelvin, is actually the same thing. So for this chapter, when we're doing calculations, it doesn't matter whether you do Celsius or Kelvin, the problem will work anyway. Now, the one mistake students make, sometimes they change from Celsius to Kelvin at the wrong time. If my temperature change is from 25 degrees Celsius to 30 degrees Celsius, I can leave them both in Celsius, I can change them both into Kelvin, but what you don't want to do, students will sometimes subtract the 2 temperatures, so 30 minus 25, it's a 5 degree change, and then they'll take the delta T, the change in temperature, and they'll change that into Kelvin. And it's like, that's not a temperature value, that's a change in temperature value, okay? And that's a bad idea, don't do that, okay? So, specific heat, typically just leave everything in Celsius and everything works for this chapter, okay? But it's gonna be 4.184 when we're dealing with water in the liquid form. If you work a problem that involves gold or aluminum or sand or any other substance, you're gonna have to look up the specific heat to plug into that equation, Q equals MC delta T. Okay, so I'm going to cut off the video and we're going to start working problems in video 2.